So we're coming into like the last of homework 4 work. Last time we took a break from like looking at angular momentum and all of that and jumped into like how do you prevent in this case it was the Francis Scott Key Bridge, where a 980 foot long 96.5 million kilogram cargo ship hit one of these supports for the bridge, and the whole thing instantly collapsed. Like the collapse took less than like 2 or 3 seconds. So as engineers, we were kind of like, all right, could we have stopped this? And the answer was like, maybe. With the right tools, maybe we could have built something that could have stopped it, but with that much momentum, even just moving 8 miles an hour, like 3 meters per second, just so much force, and so over a distance or force over a time, very hard to like change that kind of thing. Now I think we have that chapter 9 problem coming up for today. Oh yeah, 9:14. That's right. Okay, so with this problem, our main goal is like there's a marble and it's gonna roll off of a table. We want to know how far the marble can get, like after it rolls off the ramp, transitions to the table, and then kind of marking things down. It's like dot, dot, comes down here, dot, 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 comes to here, and then something happening until it reaches destination D. So as we're thinking about this, I like to think about it and like split it up into small problems that are easy to solve, rather than trying to solve like plug everything all in at once. But that would require splitting it up into little problems first. So I want to know like what your initial thoughts on trying to figure this out would be. What do we need to know? We know like the height and the width of the ramp, and we know how tall the table is, like all the H1, W1, H2, those are all known values, but what else do we need to solve this problem? What kind of stuff? What kind of equations or anything like that? Trying to figure out how far off the table it will reach. Not sure. Okay. Yeah. So you think you could have like kinetic potential energy for the 2 halves or something instead of equal to each other? Yep. Okay. Yeah, like kinematic, giving like total distance. Okay. 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 Yeah. Like rotation plus translation. Yeah. We know it's like okay. Energy conservation. Okay.
Well, we like to pursue perfect person, assume perfect person.
What's perfect Christian?
Like it's not, there's no slippage of that.
Okay. Yeah.
No
Goals
slippage.
without slipping. Yeah. Yep. Yeah, that makes sense to me. Yeah. What equation?
I just know of an equation. I don't remember what it is off the top of my head. I don't know what it's about. But there's an equation for velocity at the end of the ramp. Based off of the rolling ball.
Okay. Yeah.
And assuming there's no loss in velocity in a straight section, you could just do the math for velocity in the x direction at the bottom.
Okay. Yeah. All right. So far, and I'll come back to this half of the room in a second, but so far, some of the approaches are like this conservation of energy. So like, if we call this position 1, maybe I could call this position 2. T1 plus D1 plus work from 1 to 2 equals T2 plus V2. If I want to just put it all in one big equation, like, all right, I'm going to have some kinetic, some potential. Well, initially I have 0 kinetic. I'm releasing from rest, but I do have potential. And it's going to roll, and then now it's got a lot more kinetic energy, something like that. You think? And maybe you had, I think, I'm kind of like summarizing some of the stuff, but some people were thinking like, all right, maybe I could use T1 to like T1 prime, like the end of the table, but then also another conservation energy coming off the table. So question about this, does it matter what the slope of the ramp is? Yeah.
If you're looking at it in terms of the potential energy, only the height.
It's only the height, right? So in terms of like, if we say that work is 0, so like whether this ball rolls down like almost a vertical ramp or it rolls down a ramp for like 600 meters, it wouldn't matter, right? Because the only thing that comes into account is that h. Is that true? Like if something's rolling off of a ramp, does the slope of the ramp affect how it's going to move forward? need more like demo materials, right? Oh, I do have a car. Nice. That's a good demo material. Oh, yeah. Ooh, could this work? Now I just need something to land on. All right, so like, car going down like shallow ramp doesn't seem to like, not a huge effect, right? But what if the ramp looks like this? Is the car going to travel the same distance off of the piece of paper? No. No? Not as impressive, right? What happened? What's the difference? I mean, all right, I did drop it higher, but let's drop it lower. So same height, different slope. What's happening? What's the difference? Yeah.
Is that the same height though?
You want better, let's keep track of the data, right? We need better processing. All right, so let's say we're gonna go from here to here. Why is the magnet failing now? All right, so it's going one notebook down. Move pretty fast, and now let's do one notebook. It's like right here. But still coming to a stop. So even with same height, there's definitely a difference in how my forward momentum is conserved, right? What's happening to my momentum? This is the same thing. This is like how speed bumps are designed. They change your momentum just by changing the direction of how you're traveling. What do you think? How could we, can we do it with energy balance? Because somehow our speed is changing. Like in one case, the car came to a stop. In another case, it like kept moving forward. How do we capture that? All right, so we got our car. It's a little thing like this. Initially, it was moving down the ramp at MV, let's say, whatever, at some slope, alpha. The notebook does not apply any like left-right motion to it. Like it's the only thing it can do is really push against it. Like whatever the reaction force it needed to stop it from crashing through the notebook, that's how much force I had. That's the impulse that was created. And then overall, there's some final like MVF that is now moving forward. Kind of makes sense. So this is, at least this is one way that we could do it. There's lots of different ways that you can approach dynamics, but one way you can think about like either a speed bump or a ramp or any of these things, because the speed bump is the same problem, right? I'm driving my car, got my sweet truck now. I'm trying to go 20 miles an hour, but the speed bump is there. So I was doing this. Now I have to do that, and then this, and then overall. So initially I had whatever, V0. Then as I come down to this one, I'm gonna have some like V final that is a fraction of whatever I started with, depending on how steep the angles are. If it's a 90-degree speed bump, it's not a great day for the truck, because now all of my velocity had to go straight up and then straight down, so my VF is 0 going forward. So again, not great. Also not totally nice of the town to do something like that, so usually it's more like 10 or 15 degrees, so that you go up, you come down, slow down a little bit. Maybe get your teeth knocked in just a little, depending on how fast you're going. So with that, like, there's going to be, so I bring that up because those kind of impulses, like that impact, is doing work on the system. It's taking energy away from all that mechanical motion. So there's going to be some like non-conservative term. So I can't say that that non-conservative work is 0. Like there's gonna be something there. I can split it up into different steps where that work is 0, but when there's an impact like that, big change in velocity, I have to have something accounting for that. So anyway, one thing we could do is say, let's go from 1 to 2, where 2 is the bottom of the ramp. So I get as much velocity as I can get from the ramp, and that's going to be like my V2. And then afterwards, there's going to be some V3. We're going from V2 to V3 is just due to the table changing our velocity. And then finally, we can say we roll some distance. Now we're moving at V4, and V4 is going to bring us now a projectile motion kind of problem until we hit the floor. At least this is how I kind of think about and break these problems down. There's other ways to do it, but it works, gets you there. But when you're, so think about like how you break down these steps. Like what are the equations that you would like set up here? Like are you conserving things? Do you need like F equals ma? Is it all impulse momentum? How do you want to approach it? Oh yeah, now this is going to be 5, right? Kind of splitting it up that way. No. Oh, how to figure it out? That one we can get there. I guess as long as we identify like something happens, then we can start asking questions about what happened and how to describe that. Yeah, the nice part is that exponent, since there's like kind of a y component and x component, there's nothing happening left and right. So whatever vx I had before, I have that after. I only have upward impulse. Well, if it's constant speed, then that would only happen if it was like a smooth, like rolling transition.
Oh, okay.
Like the normal force is always. Yeah. But when you have like a sudden change, Yep. Yeah, up at one, like at the top of the ramp, it's not moving. It's going by the bottom, moving as fast as it could. Yeah, once you get that, like, yeah, that makes sense. Yeah. Now it's kind of like a standard projectile problem. Yeah. What were you working on? Yeah, and that makes sense to me. Trying to figure out what happens at the speed is one thing. There's some kind of transition, like something happens, change direction, and figure out projectile. Trying to solve it all in one equation. Okay. Like going from 1 to 2, well, it's still on the lane. You know how to figure out how fast it's moving as it drops moving, right? Okay. So usually, like we've got like, now we have 3 different tools. We could solve some of the forces, so then for the MA, and we say, all right, acceleration is this, and we integrate that. If we use energy and work, then that one gives us an equation that's always position and speed. So how fast are we going at a given spot? And then the last one is impulse and momentum. We have changes in velocity. What will they interact with the creating those? So it's usually, at least like that's how I kind of divide them up. Which one do I want to use? So in that case, if I know I dropped given distance and I know how fast I'm going, energy and work, if I look at that equation, it should give me one equation to tell me how fast I'm moving.
Yeah, but I think that's the concept. Like, I'm kidding.
Yeah,
But I don't know, we did, it might be, but we did something like this.
Okay, yeah.
Right, and we'll probably do it again.
Yeah, and then, so this force of friction is gonna be equal to whatever it takes to
Yeah, yeah.
and then some of the moments are that count.
Yeah.
And then, but then there's a relation that your distance that you travel is on times AS, so the accelerations are times theta delta. So then angular acceleration, like I times that angular acceleration. Yeah, once we get like off the table, right? Yep, then we can do
When I'm doing some research about it.
Okay.
When I first looked at it, this is what I had.
Yeah.
It's kind of just like, this was their energy company.
Yeah.
And this was their schematic company. Yep. But this area, like fuzzy. Yeah. So that's what I'm trying to figure out. Actually not bad.
Good time for a nap. Yeah. But if you know the course, you know your traveling distance. Alright, cool. Let's do some of this. Grid bar. Alright, so getting from 1 to 2, it seemed like most people were trying to, like, well, I think some people were getting hung up on, like, how do I get from 2 to 3? Like, if I know there's a change in velocity, how do I know how much of a change it is? It's like, we'll cross that bridge when we get there. Like, first we can either work backwards or work towards it, like doing a maze or a Sudoku puzzle, right? Get all the pieces and see if everything fits together at the end. So getting from 1 to 2, I could say T1 plus V1 plus work from 1 to 2 is T2 plus V2. If I'm rolling, then the work done by friction over this tiny little ramp, probably negligible, probably almost nothing. Unless you're like really, if you really want to look up like, is this a wooden ramp? Is this it says that it's a marble. So if it's a marble rolling on a wooden ramp, you can probably look up what the rolling resistance is. It will have some almost immeasurable effect on how fast it's going, but for now, let's just say it's 0. Initially, I'm not moving, so I have no kinetic energy, and I have MGH1, at least getting, if I think of it as like the table as my 0 point of like how much potential energy is 0. All that's going to be at the end, because I said the table is 0, I have 0, 1/2 MV2 squared. What about the fact that I'm rolling? Does that, yeah. Yeah, we can add like a 1/2 I. So the translational kinetic energy is that 1/2 MV squared. And then the fact that you're also rotating, now we've got a 1/2 I times like omega. Yeah, omega works, or theta dot. We could try omega. Like that. But now I've got one equation with 2 unknowns. God, darn you, Professor Cooper, and your terrible traps, equation traps. Do we have any constraints on motion though? Like, how does rolling work? If I'm moving really fast, do I need to roll really fast? Or if I'm not rolling, can I move? No. Like in order, if I want to move forward, I have to roll forward. So there's got to be a direct relation between forward motion and rolling motion. Yeah.
Convert the I omega W by like multiplying by like E squared over R squared.
Yeah. All right. Nice. So if you think about, let's say I start with this thing pointed there. Let's point it this way. Then I want to move it forward. I had to rotate by that amount. So I rotated here. It's kind of like a negative theta because I'm rotating into the page. Like that way. So distance is r theta. Velocity is r theta dot. Acceleration is r theta double dot. So I've got anywhere I have, or sorry, we used omega, didn't we? R omega, like that. So anywhere I have omega, I can replace it with like V over R. Like that, V2. So now I have one equation, one unknown, much better. And NGH1 equals 1/2 M times 1 plus, what is it, MR squared over 3? No, 2/5 MR squared. It's a table lookup, right? Lists of moments of inertia. Where's my list? I need my list of moments of inertia.
The ball, right?
Yeah, it's just a ball.
7/5 MR squared.
Wait, 7/5? No, 2/5. 7/5? I think it's 2. At least that's what I have here. 2/5. What I was trying to show you, like, you can always look it up. Like, if you know that there's a moment of inertia, there are ways that you can derive it. And if it's some kind of weird shape, then you probably want to do it in a CAD software. And then those have automatic like moments of inertia calculators. If it's something simple like a marble or a tennis ball, you can model them as either solid spheres or thin spherical shells. So 2/5 V2 square. Oh yeah, because this is an R squared over R squared. So we end up with like a n times 1 plus 2/5 V2 squared. All right, so we have a way we can get that V2 value. And then on the other side, when we know that there's that V4, once we have that value of V4, we know that we can say, all right, it's got an initial y velocity of 0. It's going to fall for so many seconds, so it'll travel this many meters in that many seconds. So from 4 to 5, I think you've done it a lot, but getting from mv2, so right when we're traveling at velocity 2, we're moving down the ramp. Something's going to happen, and then afterwards we're going to be going mv3. like only along the ramp. And the only thing that's like impacting our object is the table. So it can only apply like a force up. Like if it was like a bouncy ball, then it would apply a force up and then it would start bouncing along the table. If it's like a wooden table, it's probably going to create enough to just stop it from going through the table. Yeah, sorry, go ahead. That one would be like an impulse, yeah. And it's a really short period of time because it's not, you're not watching like the table deform and then slowly reform. Like there's not like a whole equation of motion that we're looking for. It's just something happened almost instantly, and now life is changed. Everything is different now because we went from the ramp to the table. Not a huge difference in your life, like maybe you haven't even thought about that monumental change in velocity for this little marble rolling along the ramp and the table, but instant change. But take a look at what are like the X and Y components here. So like what's the X momentum balance versus the Y momentum balance? How much momentum do you have before and after in the X and Y directions? I guess here, I'll give you. And then what is this? H1, 0.2, and 0.4. So we know the slope before, and then kind of slope after, and then direction after. Yeah. Okay. Yeah. Can't transfer that. X is Y. Yeah. Yeah, you're right. Like at the end, when we have that X. Okay. Oh yeah, using like this as a cosine. Yeah. That makes sense. Initially, when we had the X component from that E2. Yep. Okay. Makes sense. So I saw like this angle kind of get labeled like theta. It's our favorite angle, like letter. So whatever that MV cosine theta started off as, that is my MV3, because there's no force acting along the x direction. And then for bonus, for extra brownie points, I guess, that MV, I guess really like a negative MV2 times that sine of theta plus F delta T is all 0. So if I wanted to know like what was the impact on the table, well, the impact was whatever that sine component was. So that would tell me, yeah, if I'm using like a lead marble, dropping it 10 meters. When I was a kid, my brother and I like to like make our own radio shows. We'd record, like tape record ourselves on actual like tape recorders. And one of the things, we wanted a sound effect of like something falling down the stairs. So we threw a golf ball down the stairs, and as it was bouncing, it was like leaving marks because the stairs keep going down, so the height keeps increasing. Your potential energy keeps going up as it bounces forward along. So you hear the ball get louder and louder until you hear our mom yell, "I'm gonna kill you!" And then that was the end. Then it quickly cuts. Sound effect cuts off. But anyway, so you can figure out how much that marble is like leaving a dent on your table with this second equation, with the y impact equation. And now we've got our V3, right? So V3 is that same 5, and I'm using all the, just trying to be fancy, times that cosine theta. So our 0.4 over square root 0.2 squared plus 0.4 squared. Like where cosine theta is going to be a little mix of trig and Pythagoras theorem. So now I've got my V3. Going from V3 to V4. No change in potential energy. No impact happening, right? Like it's just rolling along the table. So maybe we could say there's rolling resistance and there's a slight drop in that velocity, but it's probably pretty negligible. I don't think we would see a difference. Whether the table is like 1 meter long or 2 meters long, there's probably not a huge difference in its exit velocity as it leaves the table. If we're talking like a 1 meter table versus a 100 meter table, then yeah, now let's factor in that rolling resistance and we'll see what the difference is. But this is pretty short. I forget how long this table is. W2 is 15 centimeters. Like, all right, we're gonna forget about that rolling. Just ignore that rolling resistance. I mean, you don't have to. Sorry, I'm saying we, as in like, this is what you have to do, but you don't have to. Do however you want. So we have V3, which means we have V4, which means I have 5GH1 over 7, 0.4 over 0.2 squared plus 0.4 squared. So how far am I going? And I think this total height that it drops is 1 meter. Like a 1 meter tall table. We got 2 minutes. We can crank out. Yeah, kinematically, but because it's going to be in free fall the whole time. So G is 9.81, and initial velocity is 0. That is y velocity is 0. So then solve for when drop is 1 meter, and that gives you a time. And then time times that v4 is going to tell us total distance. Yeah, so kind of like we know delta y is 1. 1 half g squared plus 0 is 3. Normally v0, like the vy0 t plus y0, but you're solving for delta y anyway. V0 y is v0 anyway. Yeah, same one. Yeah, I was just saying V3 is V4. Those are, so this is saying like those are data is square is going to be matched copies and this is 0.4 over you could solve for theta and then you know the equation exists, just give it to me. Oh, sorry, we're 1 minute over. We've got 1 meter equals 1/2 gt squared. T is 2 over g, right? I think I'm doing that right. So then d, total distance d, is my v4 times t, or that I'm doing all these variables. More fun to plug in the numbers, but again, just being fancy. Kind of like that. Makes sense? Oh, and I'm blocking the punchline. But all that, so like main thing from this is like always take a problem, split it up into like as many small solvable pieces as you can. Even if it feels like some pieces they're like it's missing, like you're not sure how to get from one step to the other, it's better to split it up and say like I know how to get from 1 to 2 and even from like 4 to 5. Something happens in the middle and just leave that and try to like identify maybe some other physics that are going on there. But anyway, thanks. See you on Wednesday.